Hello there. In this lesson, we are going to learn about electrochemical cells of the type that you might find in a 9-volt battery or a AA cell. And we will see that those half reactions that you were using for balancing is really what you have in an electrochemical cell. You'll have two half reactions, one for each of the terminals of the cell. And you can separate them like this in the lab and have two different parts that you can study along with this mystery section in the middle that we'll learn about shortly. So another term that's sometimes used for electrochemical cells is a galvanic cell or a voltaic cell. And this is in honor of a couple of scientists from back in the 1700s who did some experiments that led to our understanding of these types of reactions. So we got Luigi Galvani here, and he did some neat experiments, some kind of grotesque experiments using frogs' legs. And he found that if you connect them between two different metals, that the frog's leg would twitch. And so some sort of electrical impulse was being generated there. And a little more or less grotesque experiment, Alessandro Volta here, he came up with this neat pile of different metals that could provide an electrical source if you stack them up the right way. So both of these guys figured out that different metals produced this electrochemical reaction and led to our production of cells and batteries. So hopefully you remember from grade 10 and 11 that single displacement reactions also involved two metals, just like in the experiments of Galvani and Volta there. A typical one might be this aluminum, which is going to displace the copper in the solution. So you'll have the aluminum going into solution and giving up electrons, and you'll have the copper coming out of the solution and making this copper metal, which you see as the red stuff on the surface here. So that is an electrochemical reaction, of course, because the aluminum losing electrons is your oxidation, and you've got the copper gaining the electrons, which is your reduction. I'm going to use zinc and copper as an example because you can see there's bubbles here, and so there's a side reaction that's happening with this one, and I don't want to complicate things with that. So we'll use something that doesn't have that same side reaction. The zinc then will be the thing that gets oxidized, and we'll keep the copper as well. But anything on the activity series will do for this type of exchange. Okay, so in order to turn a single displacement reaction into an electrochemical cell, what you do is you separate the two half reactions. So in one half, you're going to have the copper. You'll have a copper metal, which is called the electrode, and you'll have a solution that is also containing copper, but this time as ions. On the other side, you're going to have the zinc in our case, but another metal, and also the same metal in the solution. So what happens then is at this side of the reaction, the copper ions will then turn into a solid copper on this electrode, and that's going to be taking electrons. The other part here is the zinc is going to be losing atoms into the solution as it gives electrons. In order for this whole thing to occur then, the electrons need a way to get from one of these half cells to the other half cell, and so that means they have to be connected with a wire here to get from one side to the other. The last feature is this thing called a salt bridge, which we'll get into a little later, but it is very important to keep the charges the same on either side so that the electrons can keep flowing. So some terminology that goes along with electrochemical cells. The side where the electrons are being given up, that's called the anode. Right? So this is the anode. And then the side where electrons are being accepted, that's called the cathode. Cathode. So cathode is where the reduction takes place, and anode is where the oxidation takes place. So the next feature to look at here is the salt bridge. This is usually some porous material that allows ions to flow in either direction and contains some ionic compound or salt. I'm going to use good old sodium chloride, but any ionic compound will do because it'll have a positive ion and a negative ion as long as it is soluble and can move either way in the salt bridge. So the salt bridge's function is to keep the charge on either electrode neutral. So looking at the anode here, we've got zinc giving off these zinc ions, right? And so that means that the charge of this solution, this whole electrode, will end up being positively charged as this reaction proceeds. So in order to keep this neutral, you're going to have to add something to neutralize that extra positive charge. So that means these chlorine ions are going to migrate this way and neutralize that side. Likewise, on the other side here, we're losing positive charge. And so this makes this solution more negative as this reaction takes place, right? Because you're going to be losing these copper ions out of the solution. So in order to balance that out and make it more positive again, the sodium ions will migrate this way and maintain a neutral charge in this solution. So that's the function of the salt bridge. Now you might have already recognized that if we're adding copper ions to the side here from the solution, we had copper ions in solution and then they gain some electrons and they become copper atoms, neutral atoms. That means we're adding solid to this copper electrode. And so the mass of this side, this cathode here, is going to increase over time as you add more and more of the solid. On the anode side here, you have the opposite happening. As this reaction proceeds, we're taking some of this solid zinc and turning it into ions in solution, which means the mass of this side is going to decrease. So the anode side will decrease mass, and the cathode side will increase mass. These are called active electrodes because they're constantly changing their mass due to the added or removed atoms. Okay, so not all electrochemical reactions or half reactions require a solid to be included. Here we have one that does. We've got copper giving up electrons and becoming copper 2. So that means this here is the anode this time. And over here we've got some iron 3 ions taking an electron and becoming iron 2 ions. And so this will be our cathode this time. And so the side where ions are just becoming other ions, we don't need to have an active electrode. We don't need any place where iron is being added to a solution or taking out of it. And so what we'll use instead is called an inert electrode. And that'll be this thing here. And it is usually platinum that's used to do this. And so in this solution, you'll have the iron 3 ions, and they will touch that inert electrode and pick up electrons in order to become the iron 2. So electrons going to come in here and be given to the iron ions in solution, but you don't add any mass to the platinum because the new ions are also in solution. So no mass change. That's what they mean by inert. The other side is an active electrode. And so just like the previous example, here we have copper atoms on the electrode, and then they become copper ions in the solution. So the mass of this electrode will decrease over time. So mass decreases. And as it does, the electrons leave and go to the other side where they're picked up. Alrighty, so to summarize, the parts of an electrochemical cell are often put into this line notation where you list the parts of the anode and cathode half cells. So you use a single line between the parts of one half cell and the other, and you use a double line to represent the salt bridge and the separation between the anode side and the cathode side. So for this guy here, we have the zinc here giving up electrons, so it's the anode, and we've got the copper as the cathode. So we're going to put the zinc anode, and then a line, and the electrolyte, that's going to be the ions, and so it's just zinc ions in there. And then you put the double line for the salt bridge. And then the other side, the electrolyte, is the copper ions in solution. And then the copper solid is the electrode. All right, so for an inert electrode, works pretty much the same way. This time the copper is the anode and this iron is the cathode. And so here you would put the copper solid again as the electrode, and then the copper ions as the electrolyte, and then the double line for the salt bridge. And then the electrode on this side has both the 3+ ions and the 2+ ions. And then the electrode is an inert one, which we'll use platinum just as our go-to. And so that would summarize what's going on in this cell. Alrighty, so let's go through everything we've learned today. If we have set up an electrochemical cell here, and we've got gold on the one side and we've got magnesium on the other side, and we got a reaction here where gold ions are becoming the gold solids. We got Au 3+ ions here are going to plate onto this electrode. So that means they're taking electrons to do that, so that makes this side the cathode. On the other side here, we got magnesium metal becoming magnesium ions, and that means this side is the anode. The electrons then are going to flow from the anode through this voltmeter to the cathode. Right, so that makes this the negative side and this the positive side. And then we're gonna, let's see what we've done here. Moving of electrons, check. Moving of ions in solution, we got them going in and out, check. Salt bridge, so this side is going to be losing, the cathode's losing these positive ions, so we're gonna replace them with the potassium, so it's gonna go this way. And we are making this side more positive because we're adding positively charged ions, so to keep this side neutral, the negatives are gonna go this way. Great, so we did the ions in the salt bridge. Labeled the anode and the cathode, we did that, anode and cathode. Now we're going to do the line notation. So anode goes first, so we're going to put the electrode, the magnesium solid, a single line to show the phase change. And we got magnesium ions, then we got the salt bridge. On the other side we've got gold ions, and then the phase, and then gold solid. Oh, I forgot my little AQ here. Great, there we go. We did the line notation. We figured out the anode and the cathode. We got the salt bridge, the ions in solution, the movement of electrons. Got it. All right, good luck with your practice. Hope that helped. We'll talk to you soon.